This is part 4 of the equilibrium lab, force table lab experiment. Now, the addition of the vectors, these are the 3 vectors that I'm adding. I've erased the data over here. I actually have them off screen, but these are the 3 vectors that I am adding. Now, when you're adding vectors graphically, you're using the head to tail method. And so I need to start with one of the vectors. There's another video, PowerPoint, that deals with this in more detail. But I'm going to take one of these vectors as a starting point. Now, I have this original up here. If I were doing this on paper, I would have, personally, I'd have a separate sheet of paper where I was doing this. But that's not what we're doing right now. And so, there's the marker I want. So I'm going to pick a starting point. Now I know how much space do I need going up and down. Well, if I pick a starting point, that's as far up as I'm going to go. So I'm going to pick this as my starting point. It's almost arbitrary. It's around how much space do you need. So that's my starting point. I have to establish 0 as before. And so now ideally, if this were graph paper, I would make it parallel to this line right here. This is my 0 mark here. I'm going to do it by eyeball, so you get to see a videotape of my back for a moment. And so I'm establishing a baseline right here that's 0 degrees. Now, it's not necessarily drawn perfectly, but this is one reason why I recommend using graph paper, at least line paper, somewhere where I know what it's easy to spot parallel lines. Now, if I were truly retentive on this one, I could then measure the distance here and the distance there, make sure they're the same. But I think that's a whole lot of time that could be spent elsewhere. So I have 0 degrees. I'm going to draw this one. Now, the line that I'm about to draw is going to represent F3, and it needs to be as long and in the exact same direction if it's the same vector. So it's as if I'm just shifting this upwards, except I don't have that magic ability just to shift this upwards, and so I have to redraw it. I know it's a 30-degree angle, and it is 65.3 centimeters long. And so again, I establish my 30 degrees right here. .3 centimeters long. If I started up too high up on the board, I'm about to go I'll go off the board. And let's do it this way, where I'm going to start at 65.3 centimeters. And again, excuse my back. And it slipped. 65.3. All right, I'm pressing down hard on this one so that it stays in place. That should be as long as this one is, and it should be parallel. It starts a little bit back, it ends a little bit back. Those aren't bad. Now, the next one, when I'm adding vectors, again, it's the head to tail method. And so this is my new starting point right here. It's like if you're traveling, if you're going from one place to another, you would go up, over, and down. Every time you change directions, you're changing directions from where you last were, not from the starting point, but from where you last were. If I go north and then go east, well, when I was traveling, I went east based upon where I was after I went north. Well, the same type thing is going on here. I went off in this direction, and so now my next change is based upon where I am at that point. And so I have to establish 0 again. And this is where graph paper becomes really, or at least line paper. This line needs to be parallel. This line up here needs to be parallel to that line. And so I'm going to have to eyeball it as best as I can. Now, it is not necessarily parallel to the top up here, but it should be parallel to this line right here. And I think that's parallel. I'm just drawing a dotted line there because, again, all I need is the reference. So for my next angle, I got my 0 degrees right there. I'm now going to do F2. I could do F1 next. I'm just picking I'm picking F2. Just that's my whim. And so I know it's at 185 degree angle. See the previous videos for verification of that. And so I know it's 5 degrees below the horizontal. So I put my mark there. That's 185 degrees. Again, that is 185 degrees. And so now I draw my line. Again, it should be parallel and just as long as this one. The length using our scale is 49 centimeters. And so again, there it is, 49 centimeters in that particular direction. And that's F2. Again, we have F1 here. I need to label it. F2 here. I'm labeling that one. On my vectors, I am drawing the heads because direction is incredibly important. You need to indicate to the reader the direction that you're going in. So now I'm here. So this is my next starting point for when I add the next vector. So again, I have to establish a 0 line here, and it needs to be parallel to the other two baselines. And I'm going to try to make it parallel to the top one because that's easier to see. Oops. Slipped a little bit. All right. So I've established this right here. I now need to, again, similar to what we did in the last video, it's going to be 73 degrees into the third quadrant. And so establish this right here. I think my baseline's a little bit high. So I'll cheat it down just a little bit. So 73 degrees. I'll make my mark. And so this one needs to be 32.7 centimeters long. All right, and that's where I end up. Now, I haven't come up with my final answer yet. All I've done is I've just written down the sum. Again, the equivalent would be if I asked what is 2 plus 3, and as a response you did 2 marks here and 3 marks there, and you left it like that. You haven't answered the question. You've set it up for answering, but you haven't added them up yet. So the answer in this case obviously is 5, but I want to emphasize the fact that when you're adding vectors, you do need to come up with an answer. Now the answer when adding vectors, it is a vector from where you start to where you end. You're trying to find the equivalent vector of adding all things up. To me, visually, it's better with directions. So I go this way, and this way. Well, where do I end up relative to my starting point? Well, I started here. I ended here. And so I am drawing my vector. That is my resultant vector. I am marking it as such. Let me draw it bigger over here. It's sort of redundant there to have the double print R as well as the vector symbol, but I did it anyway, so yeah, that's just the way I roll today. So I need to figure out, now I've drawn my vector, now I need to figure out what exactly is that force. Now ideally, if I were in equilibrium, the sum of the forces should have been 0. I should have ended up exactly where I started. But in reality it's not going to happen. And I knew that before I walked into it. I made sure that didn't come out perfectly, even if I'd done it perfectly. So now I measure the length of my resultant. And it is it's 3.4 centimeters long. And now I have to figure out what does that mean in terms of force. Well, I have to go back to my scale. My scale was 1 centimeter is 0.03 newtons. And so, let's set up, so 3.4 centimeters times 0.03 newtons over 1 centimeter. My centimeters cancel out, so 3.4 times 0.03. If in doubt, given my scale, my centimeter number needs to be bigger than the Newton number. And so whatever I do, I'm going to multiply or divide. Whatever I do, I need to make sure that the number of newtons, that number there, is less than the number of centimeters, just like in the scale. And so I do 3.4 times 0.03, and I end up with my resultant. Magnitude of my resultant is 0.102 newtons. And, okay, unless I made an error in my calculation, okay, I'll deal with that. And then I have to find the direction, because again, the resultant, we are dealing with a summation of vectors here. And so my final answer is a vector, which means I need a magnitude and a direction. So that's 3.4 centimeters. That should be, sorry, just doing a quick check here. 3.4 centimeters. This line right here was 32.7 centimeters. This is 3.4. This is about a tenth, roughly, a tenth of this right here. And so my force is about a tenth of this force right here. Again, the F1, oh, got the label mistake there. That should be F3. This is F1. F1 represents 0.98 newtons. This is about a tenth of that, so the length is about a tenth of it, so it's seeming right. To find the direction here, well, my protractor is not small enough to deal with this. And so what I'm going to do is, that's my resultant right there. I'm going to take some light color. Now, I know this green is almost faded out. I'm going to draw put it right there. And I'm just going to put a dashed green line after it. Now, if you can't see it, that's great. If I were doing this on paper, I probably would be taking a pencil and very lightly putting a dashed line to indicate it's not part of the vector. It's just there to indicate direction. Now I can take my protractor and I line it up, and it is hitting at the 25-degree mark. Actually, pretty darn well at 25 degrees. Hitting at the 25-degree mark. Again, my angle is always from 0 going counterclockwise. Why? Because that's what they did when they established this thousands of years ago. So I know this is 25 degrees. That's 180. So my angle's got to be the sum. So the angle, so that's 180 degrees. This is 25 degrees. And so my resultant here, and let's get rid of some of this stuff. My resultant is going to be 0.102 newtons and 205 degrees. That is my resultant. And that is how you add vectors graphically. It's been a whole lot of fun, as I'm sure, as you've gone through it and all the joy of it, but just make sure the more precise you are, the better the results. If you slop something down, then slop's what you're going to get out. So thank you very much. Have a nice day.